Most volunteer management software operates as a digital sign-up sheet. Project NEXUS version 1.5 requires a more rigorous architectural tier. Embedded within a multi-tenant time-banking platform, NEXUS models human availability and tracks physical endurance across thousands of distinct shifts. The engine relies on a massive underlying structure: 35 database tables, 14 dedicated PHP services, and over 82 API endpoints. We are going to deconstruct how this architecture is built, starting with the base temporal data models and scaling up to the algorithms that predict human burnout. When hundreds of concurrent users compete for highly constrained time slots, standard MVC development fails. High concurrency environments require engineering for human optimization at an enterprise scale. This schema relies on two primary entities: the vol opportunities and vol shifts tables. Vol opportunities define spatial and operational boundaries, storing geolocation coordinates and required skills arrays. Below it, vol shifts dictates temporal boundaries, breaking opportunities into slotted times with strict capacity integer constraints. This capacity integer creates an immediate engineering bottleneck. If 50 volunteers attempt to claim the last remaining slot at the exact same millisecond, the system must decide the winner without corrupting the state. To prevent capacity overflow, the engine utilizes a database transaction with an explicit row lock. The record is physically locked from other queries until the first transaction confirms capacity and commits. Establishing strict data integrity at this base temporal layer is the prerequisite for every downstream algorithmic function. With the temporal data structured, the system can begin the process of deployment optimization. The volunteer matching service runs a find matches algorithm designed to pair the right human with the right role without manual intervention. It evaluates every potential candidate on a 100-point scale, broken down across 3 distinct dimensions. The first dimension allocates 60 points purely for skill alignment. The backend executes this by parsing the required skills array and running case-insensitive substring comparisons against the volunteer's profile data. The second dimension allocates 30 points to analyze the user's experience, based on the total volume of their previously approved hours. The final 10 points are awarded as a logarithmic activity bonus. The formula adds 5 to the logarithm of hours plus 1, then multiplies the result by 2. This specific logarithmic curve prioritizes highly engaged users without creating an insurmountable barrier for newcomers entering the system. By weighing skills, experience, and recent activity, the engine transforms subjective scheduling into an automated deterministic function. Hyper-efficient algorithmic deployment at this massive scale carries a very high, unavoidable risk: the inevitable burnout of the physical human worker. The Volunteer Wellbeing Service utilizes a dedicated Vol Wellbeing Alerts table to monitor this failure rate through 5 distinct risk indicators. The first indicator evaluates the user's shift frequency trend. A 50% drop in activity over the last 30 days generates 20 risk points. The second indicator parses the Vol Shift signups table to calculate cancellation rates. Exceeding a 50% threshold adds another 25 points. The third and fourth metrics track significant reductions in total logged hours and engagement gaps lasting longer than 60 days. Finally, the engine scans for overcommitment. Having more than 7 confirmed shifts in the upcoming 7 days adds 15 points, pushing the total risk score past the critical threshold. When a volunteer's aggregate risk score reaches 30, the system persists a critical alert to the database. This alert triggers a routing consequence, automatically notifying the organization coordinator to physically intervene. True enterprise architecture must always account for the slow degradation of its most critical physical assets, the fragile psychological endurance of the human volunteers. Protecting those volunteers requires the system to transition from predictive logic to physical attendance verification. The architectural challenge is verifying physical presence in decentralized, untrusted environments without constant admin oversight. To solve this, approved applications automatically trigger the generation of a secure 32-byte random hex token. This token is immediately inserted into the Vol Shift check-ins table, where it sits in a pending state. The QR check-in operates within strict temporal boundaries. The token is only valid exactly 30 minutes prior to the shift start. The token follows a closed lifecycle. First, it is applied, then safely scanned in, and finally scanned out. Binding cryptographic tokens to these narrow temporal windows effectively eliminates attendance fraud without manual supervision. The final architectural requirement addresses legal and behavioral safeguarding compliance. In this environment, physical safety must be a structural database constraint rather than a UI element. Onboarding triggers, such as requirements for vetted interaction, are captured by the system and merged downward via OR logic. The output of that logic feeds directly into the core user messaging restrictions table, locking specific data pathways at the database level. The API enforces these broker approvals at the schema layer before any messaging or exchange action can be processed. This tight coupling connects the isolated volunteering module directly to the core timebanking exchange system. Embedding legal restrictions at the schema layer enforces compliance by design, creating a structural barrier between the platform and potential liability. This view shows the completed Nexus architecture in its entirety. Isolating complex domains like matching logic and burnout tracking into separate services prevents the system from collapsing into a monolithic deadlock. The engine seamlessly processes quantitative organizational metrics alongside qualitative human realities. Enterprise software design requires a structure that mirrors the operational, temporal, and legal physics of the real world. True architectural elegance is only achieved when the system accurately models those physical realities.